Okay, so in the last session, we studied about single linked list, how to implement a single linked list, and we have implemented few functions of single linked list. And today we'll continue with that, and we'll be implementing few more the functions or operations on single linked list. And today we shall complete the implementation of all the operations of single linked list. Okay. So we are done with insert at end function. Then we are also done with insert at beginning, and then we we are done with display function, and then we have our main function. So now insert at end is done, insert at beginning is done. Now what can be done? Insert after a given node, and then one more possibility, insert before the given node. Okay. So there comes around four possibility for the insert function. First, insert at end, insert at beginning, then insert after a given node, and then insert before a given node. Okay. So we can implement one of the two functions, that insert after a given node or insert before a given node. Then the remaining function can be done by you, and then we can start with the remove function. So again, then we have different possibilities for the remove. Remove the last node, remove the first node, or remove the given node, or remove after a given node, or remove before a given node. So there are different possibilities for the remove function also. Okay. So let us see how to implement insert after a given node. Okay. So here what we'll be doing, we are going to write a function which will accept a linked list in which the insertion has to be done, then the data to be inserted, and then the third argument, that a key value after which this data is to be inserted. Okay, a key value. So the key value we have to search into the given list. If the key value exists, then after this key node or the key value, we need to insert the given data. Okay, so that we need to do. So let us call this function as insert after, and then the arguments are, first of all, obviously the linked list into which we need to perform this operation. So a pointer to struct SLL. Then second, the data which we need to insert. And third is the key value after which we need to insert. So I can call it K. And yes, the return type would be same, because here we are going to change the linked list. So the return type will keep it as a pointer to the same structure, SLL. So struct SLL star. Okay, then start the function. Now, the first thing what we need to do is to find whether the given key value is there into the linked list or not. Okay, and before that, obviously you need to check if the list is not empty, then you cannot search anything. If the list is not, if the list is empty, sorry, if the list is empty, then you cannot search anything. If the list is not empty, then only you can search the given key value. And then if the given key value exists, then only after the given key value you can insert a new node. Okay. So first thing we would be doing is to check. Obviously, few dummy pointers are required, so we'll be declaring it later. First, we need to check if the list is empty. Now, here there are two possibilities, that if the list is empty, then a new node can become a first node in the list. Or if the list is empty, then we may not do anything. Okay, so two possibilities are there. Either when the list is empty, either we can make the new node as the first node, in the list. Or if the list is empty, then we can say that the given key value cannot be searched into the given list because the list is empty. So we cannot perform the insert operation. Okay. So what we do, we keep it simple and we say that if the list is empty, then do not do anything. Okay. In this case, if the list is empty, say I would simply return H, done. So H is also null, so we are returning null if the list is empty. Okay. If the list is not empty, then we'll come to this part of the function, and here we need to search the given node, and then after the given node, we need to add a new node. Okay. So the first thing we need to do is to create a new node. So for that, we need pointer. So let me declare the pointer struct SLL star P, and then for traversing, I would be requiring one more pointer, say P and P, and then here we'll be saying P equals to typecasting log size of operator, and what we need size of struct SLL. Okay, so this much space we want, and if the space is allocated to a pointer, then we can go ahead with the insert operation. So here you can perform the check. If P is null, then nothing can be done. So say not enough memory. Okay, let me do that also. If P is null, I would be saying printf new line, not enough memory. Then I can simply return the value of H. So, so here also we are returning, so no need to write here else. And at this point, we can assume that the memory has been allocated, and so I can make up my node. So I can say P of data equals to the given data element D, and P of next pointer equals to null initially. Okay. Okay. So now our node is ready. And now since the node is ready, so what we need to do, we need to search the given key element. And if the given key element is found, then perform the insertion. So for that, I would be starting from the first node. So TMP equals to H. Okay. And while TMP of data not equals to the given key value, I would say TMP equals to TMP of next. So till we do not get the given data, so while TMP of data not equals to K, the given key value, we would be simply saying TMP equals to TMP of next. Okay. Suppose H is pointing to the first node, so TMP also starts pointing to the first node. And suppose in the first node I have 10, in the second node I have 20, and in the third node I have 30. So in this case, what would happen that TMP would first point to 10, and suppose the value of K is 20. So TMP of data is 10. So TMP of data not equals to K. Yes, the condition is true, it is not equals to K. Then we will come inside the while loop, TMP equals to TMP of next. So TMP would start pointing to the next node, which is 20. Then we will go up, TMP of data not equals to K. Now TMP of data is 20 and K is also 20. So 20 not equals to 20, condition is false, will come out of a loop. So when we come out of a loop, TMP is pointing to a node which is having a data equal to the given key value. I repeat, TMP is pointing to a node which is having a data equal to the given key value. Okay? So in this case, I have got the node which is having a data k. So I need to insert a new node which is p after this node. Okay. So here I can say let me write here p of next. First, let me write p of next equals to tmp of next. So now the next pointer of the p node starts pointing to a node which is next to 10. Okay. When we write p of next equals to tmp of next, the next pointer of the p node starts pointing to a node which is next to tmp. Okay. The moment this is done, then we can say tmp of next equals to p. That. So now the point you write tmp of next equals to p. So now tmp of next point of tmp would start pointing to p. So the node p is coming in between or has come in between the tmp and the node which was after tmp. Okay, are you getting it? So this is a insertion after a given node. Okay, the node p has come in between the node which is a given node, that is tmp, and the node which was next to it. Okay, so p has come in between. How? We have first written p of next equals to tmp of next. So the moment you write p of next equals to tmp of next, so the node which was next to tmp, the p node is started pointing, p of next is started pointing to this node. Okay, then after that what we are writing, tmp of next tmp of next equals to p. So this tmp of next would start pointing to p. Okay. So this p node has come in between the tmp and the node which was after tmp. Okay. So this is your insert after the given node. Now there there are few things which we need to fix up. The first thing is what? Suppose the given node does not exist. You got three nodes into your list 10, 20, and 30. And suppose the value of k is 40. Okay. So TMP equals to h, it is pointing to the first node temp. TMP of data not equals to k, condition is true because it is 10 and k is 40. So 10 and not equals to 40, come inside the while loop. So TMP equals to TMP of next, TMP starts pointing to the next node which is 20. Go up, TMP of data not equals to k. Yes, it is not equal because TMP of data is 20 and k is 40. Come inside the loop, condition is true. Come inside the loop, TMP equals to TMP of next. So now TMP starts pointing to the third node, which is 30. Okay. Again, go up, TMP of data not equals to k. Yes, TMP of data is 30 and k is 40. Condition is true. You come inside the loop. So TMP equals to TMP of next. Now TMP was pointing to the last node, and when you write TMP equals to TMP of next, TMP of next is null because this is singly linked list. Okay. So now temp starts pointing to null, or temp has a value null. So when you again come up in the while loop, and when you try to say TMP of data not equals to k, when you try to check this condition TMP of data not equals to k, so the value of TMP is null. So this is something like null and arrow operator data, which is invalid, which is not valid. Okay. So in this case, this won't be a compile time error. Please listen here carefully. Here starts the, you can say, complications of pointer. This is not at all a compile time error. What would happen when the code executes and when there is a condition like this, where the given key value does not exist into the linked list. So in that case, this TMP of data finally would become null as operator data, which is an invalid. So your program will terminate. Okay. And on Linux machine, you may get an error, something called as segmentation violation. So your program would be terminated, and you will get a system error called a segmentation violation. Okay, because You are trying to do something which is not at all permitted, which is not at all expected. Okay. So how we can check that? Uh, let us keep the same code and let us try to execute it for a condition for which it will work, and then let us try to execute it for the condition for which it should not work, and we'll see the result. So this is insert after, and here I can say that the insertion is done. So now we can return H. Okay, so it should work. So let's go and let's go here. Let me call this insert. Or let me have one more option. So instead of this remove, I can have insert after. The third option is insert after, and we'll scan the data, we'll scan the key value, and then we'll call insert after, and we'll pass the signal. Okay, absolutely fine. Fine. Well, let me compile this code. Code is already running. This code is already running. Okay, so code compiled, and this is my exe file. Execute. So insert begin, insert after, remove after, and then display function. So let me insert something. I insert 10, and I display it. So the English content is 10, and then we have some information. I have displayed some additional information. You should not worry for this. I was just checking the size of integer on my machine and size of pointer. For that, I was doing this stuff. So you should see up to here that your list content is 10 and the size of the list is 16 bytes. Okay. Then let me perform few more insertions. I insert 20, and then I go for one more insertion, say 30. Okay. See the data 10, 20, 30. Okay. Fine. Now let's go for insert after, the third option. Okay. And I want to insert, say, 25, and I want to insert 25 after 20. So my key data is 20. Okay. Please see the things carefully here. I want to insert 25, and I want to insert this data after the node 20, after the key value 20. And if you see your linked list, so it is 10, 20, 30. So 20 is there, which is the middle node. So as per our code, it should find it, and it should insert 25 after 20. So after insertion, our list is expected to be 10, 20, 25, 30. Okay, let's see whether it works or not. Let us display it. And yes, it is working. It is working perfectly. 10, 20, 25, and 30. Okay. Now let's check for another condition wherein we do not have the key value. Okay. Now the key value was found, so the insertion was done perfectly. Now let us go for the condition. I go for the third option again. insert after, and I say that my data is suppose 40. I want to insert 40, and I want to insert 40 after say 40, or yes, 40. Now this is a key value 40, and this key value does not exist into my list if you see it carefully. So basically, what should happen that my code should give me a message that the key value does not exist or something like that. But let us see what does happen. So this is my key value, and let me hit the enter key. So it has stuck, and your program terminated. Okay. So this is what's happening on a Windows machine. The code has stuck, and it stopped there for a few seconds, and then my program got terminated. So if you execute the same code on Linux machine, so the program will be terminated, will be aborted by the system, and then you will be getting the system error, something called a segmentation violation, which is related to the pointer. So it is happening because of that reason only, which I was saying to you, that you cannot say null arrow operator data. Okay, that is not possible. Yes. Okay. So here in this case, when the key value k is not present in the list, finally your temp will be having a null. And when temp has a null, so your statement null arrow operator data is absolutely invalid. You are trying to access a member which is pointed by null, which is not possible. Okay. So in this case, we need to have some fixing which can avoid this thing. Okay. So the simple fixing could be like what? That the first check, you can have two checks over here uh, with the help of n% operator. So this is something like and. So my first check should be if my temp is not null. So if my temp is not null and at the same time temp of data not equals to key. Now what happens that the checking is always done from left to right. Okay. So when it goes to the while statement, the first checking is temp not equals to null. If temp is not equals to null and this is an AND operator. So AND operator you must be understanding. Okay. 1 and 1 will only become 1. 1 and 0 is 0, 0 and 0 is 0, and 0 and 1 is also 0. So if any of the value is 0, the output is 0. Okay. So what does it do? It has some smart checking. What the compiler does, the compiler always try to have some smart checking. And in that case, since there is an AND operator, so it will check the first condition. If the first condition, this first condition, temp not equals to null. If this condition is true, then only it will go for the next condition because this is an AND operator. If this condition is false, so it will not go for the next condition at all because the first condition is false. So obviously the overall condition, because it's an AND operator, so the overall condition will be always false. So no need to check the second condition. No need to check this condition, temp of data not equal to key. Okay. So that's why our first condition should be temp not equals to null. And if temp not equals to null, then only it would check for this. Okay. Now, after this, here we need to do some check before inserting the node. When you can insert the new node P, only if the key value is found. Okay. And when I can say that my key value is found only if my temp is not null. So if my temp is not null, then only I can have this insertion. Else, I would be saying then tap given key element or given key data does not exist. Okay, fine. This is fine. Now let us see our code properly works or not. Let me compile. It says code is running. I need to stop it. I need to restart it. Let's compile it. Okay, so it's got compiled, and let me execute this executable, and let's perform few insertion 10 and 20 and then 30. Let's display 10, 20, 30. Okay, it is there. Then insert after, and my data is suppose 25, and I need to insert after 20. Let's see whether it's working. Yes, it's working perfectly. Then I will be again going for insert after, and this time I would say I want to insert 40 and I want to insert after 40, which does not exist. So in this case, I should get an error message that the key value does not exist. So yes, we are getting a message. The key element or the key data does not exist, and we are back to our menu. Okay, so our program is not getting terminated. Now we are in a position to come back to our code, and then we can go for some other operations like I can now insert at the beginning, and I want to insert 5, and I check my link list. So 5, 10, and the link list is growing dynamically. Okay, so now it is 80 bytes. Now suppose I want to insert after, and I want to insert after last node. I want to insert after first node. So all those should also be done. So I go for the third option, and I say I want to insert 40, and I want to insert it after 30. Now this should also be done. Okay, so let me check. Yes, it is also done. So now 40 is inserted after 30. Okay, so the insert operation is getting done properly. Now one is remaining that is insert before. So I think that you people can do. And now let us start with the next operation, important operation, which is called the remove or the delete function. I want to delete a data or a node from the list. The prototype would remain same. What I mean to say, let me call it remove. By default, it is remove last. So let me call it remove last. So I can simply call it remove. Obviously, we'll be passing the linked list from which we need to remove the node. So it will be a header pointer H. Anything else required? No, nothing else required. And what this function would be returning? Function would be returning the linked list. So again, a pointer to the structure SLL. Okay, so how to remove a node? And this is by default remove the last node. Okay, so what do you need to do? You need to go to the last node, and then somehow you need to detach that node from the list. Okay. I repeat, you need to detach that node from the list. Okay. So how will we doing that? First of all, we need to traverse. So obviously, we'll be requiring a pointer for traversing. So let me call it TNP. Okay. And then we'll be checking if the list is empty, so nothing can be deleted. So if my list is empty, if h equals null, so I can simply print a message that list is empty. Okay. Else, now in the else part, when we come into the else part, we understand that the list is not empty, and now when the list is not empty, I need to go to the last node and I need to detach that node from this list. Okay, so we need to traverse. So tmp equals to h, and then while tmp of next node equals to null, till I do not reach the last node, I would be saying uh, tmp equals to tmp of next. Now what's happening that when we put up this code or this loop, so this loop will take us to the last node. Okay, this entire loop tmp equals to h, and then while tmp of next node equals to null, tmp equals to tmp of next. Okay, so this loop will take us to the last node, and after this loop, tmp would be pointing to the last node. Now tmp is pointing to the last node, and we need to remove that node. Okay, and how can we remove that node? To remove the last node, you need to come back to the second last node, or you need to go to the second last node, and from the second last node we can detach this node. What I'm saying you that the last node is pointed by the next point of the second last node. I repeat, the last node is pointed by the next point of the second last node. So if I make the next point of the second last node as null, so this last node would be detached. I repeat, if I make the next point of the second last node as null, so this last node would be detached. Okay. So basically, what we need a pointer to the second last node. So when we have a pointer to the second last node, we can say that pointer next of that pointer equals to null. And that way, this node, which is the last node that is pointed by TMP, would be detached. Okay, and then we can free it. So we need some way by which we can reach to the second last node. I repeat, temp is getting to the last node. Temp is not taking to us to the second last node. Okay. With the help of this condition, temp would reach to the last node after the while loop. After the while loop, temp would be pointing to the last node. But what we need a pointer to the second last node. And there is a simple logic for that. Let me do that. Let me have an additional pointer. So apart from temp, let me have an additional pointer and let me call it prev. So it is something like it is pointing to the previous node. Okay, so I'm calling it prev. Now, what I would be doing that inside this while loop, I would make it a while loop like this, and we'll put up this inside the while loop. But before making this temp to point to the next node, okay, what I will be doing, I will be simply writing rev equals to temp. Please see here carefully. What we are doing, we are simply writing prev equals to temp. Okay. If you remember, then I said you that the logic of this temp equals to temp of next, while temp of next not equals to null, temp equals to temp of next. This logic is equivalent to something like you are writing I equals to 0, then while I not equals to phi, and then inside it you are writing I equals to I plus 1. Okay. So it is equivalent to that only. But here we are playing with pointers. So when you have that kind of understanding, I equals to 0, while I not equals to phi, inside it I equals to I plus 1. Now what happens that after the while loop, the final value of I would be what? I not equals to phi. And inside it, we are writing I equals to I plus 1. So the final value of I would be phi. Because the moment I becomes phi, the condition fails and you come out of a while loop. So when you come out of a while loop, the value of I is phi. Okay, the value of I is phi. Now suppose I want a value just uh, previous to the value of I. Okay. So for example, finally, when I becomes phi, I want to have a value 4, which is just previous to phi. Okay. Or which is 1 less than phi. So for that, I will be having one more additional variable, say j. So I keep the loop same. I equals to 0, then while I not equals to phi, I equals to I plus 1. But what I will be doing that inside that while loop, when I am writing I equals to I plus 1, just before I equals to I plus 1, I would write j equals to I. So when I write j equals to I, and then I manipulate the value of I or increment the value of I equals to I plus 1. So j is holding the previous value of I. So when I is 0, j equals to 0, and then I equals to I plus 1, so I becomes 1. Now j is 0. So j is 0, I is 1. Likewise, when I is 2, j is 1. When I is 3, j is 2. When I is 4, j is 3. And when I is 5, j is 4. Okay. So this way, j always holds a value which is the last value of I, which is the last value of I or the previous value of I. Exactly in the same way we are doing here for pointers. I repeat, exactly in the same way we are doing here for pointers. Okay. So this is something like, let me write that I equals to 0. Okay. In a comment. And this is something like while I not equals to some value, say phi, and then here it is something like j equals to I, and this is I equals to I plus 1. Okay. So this way, what's happening that preview is having a pointing to a node which is previous to temp. Okay. So let's start from the first one. Temp equals to h. So temp is pointing to the first node. Okay. And then while temp of next node equals to null, we get inside the loop. Prev equals to temp. So prev also starts pointing to the same node. And then temp equals to temp of next. So temp starts pointing to the next node. Prev is pointing to the node which is previous to temp because temp is now pointing to the next node. We go up, we check the condition. Condition is to come inside prev equals to temp. So prev also starts pointing to the node which is pointed by temp. But now temp equals to temp of next, so temp starts pointing to the next node. Okay. So when the loop completes, when this loop completes, so after that, temp would be pointing at this point after the loop. Temp would be pointing to the last node and prev would be pointing to the second last node. I repeat, prev would be pointing to the second last node. Now, since prev is pointing to the second last node, I can simply say prev of next, which is pointing to temp. Prev of next is pointing to temp. So I can say prev of next equals to null. The moment I write prev of next equals to null, So I am detaching the last node from the second last node. Okay, I am detaching the last node from the second last node, and that last node is still pointed by TMP. This is important. That last node is still pointed by TMP, and then the way we have allocated a memory when we inserted a new node or when we created a new node, in the same way we need to free up the memory, or we need to free the memory when we delete a node or when we remove the node. Now this node is pointed by temp, so I will be making use of a library function called free, and to this library function I will be passing the pointer whose memory has to be freed, whose memory has to be freed, and that pointer is my TMP point. Okay, so now I am freeing up the memory, and then the moment I free up the memory, now I can say that this has been removed or the last node has been removed. Uh, for some safe coding, before this, let me write preview code statement. This is also important. Okay, so this is done, and now I can say that a node has been removed, and I can simply printf last node removed or deleted. And then after this, I need to return H. H should be written. Uh, let's see it for all the possible conditions, whether it works or not. Remove last function, and we have here option remove after. Let's make it remove or remove last. Okay, the fourth one, fourth case. Okay, let's compile our code. Code is already running. Need to restart it. Code got executed, and let's execute our compiled file. So if I try to directly remove something, so yes, it is handling that case when the list is empty. Then let's insert few data nodes. So insert 10, then I insert one more, so 20, and then I insert one more, so 30. Let us display. So yes, you got three nodes, 10, 20, and 30, total 48 bytes. And now if I try to remove, so this is remove last by default. So it should remove the last node that is 30. Let's see. So it's giving us the message last node removed. Now let us display the list and let's see. So yes, the last node has been removed, and now the list has only two nodes, 10 and 20, and most importantly, the size of the list is 32 bytes. Earlier, the size of the list was 48 bytes when we had three nodes in the list. Now there are two nodes after deleting a last node. So now the size of the list is 32 bytes. So this way I can say that the linked list dynamically grows and dynamically shrinks. It's a data structure which can dynamically grow and can dynamically shrink. So I can go for one more removal. Fourth option. Last node removed. Display. Yes. Only one node remains. And now we need to see carefully whether this condition works or not. When the list has only one node and when you are removing that node, so the list should become empty. Now our insert function, sorry, our remove function is capable of handling this case or not. Okay. So let's call our remove function once again. Fourth option. It says last node removed, and let me display. Oh, here comes the call. So it was saying us that the last node has been removed, but when we tried to display, so this is the output which we are getting. Now it has become an infinite loop. So in short, earlier our display function was working perfectly, but when we call the display function after calling a remove function for a single node, I repeat, after calling the remove function for a single node, so it has created a problem. So where is the problem? The problem is in the remove function, and the problem occurs when you have only one node in the list, or what you can say that the list should become empty after the removal of that single node. Okay, so we are not handling that case. Now let us see where we are missing that case. So this is our remove last function. The list is not empty. The list is having a single node. So we come to this part. TMP is pointing to that single node. Prev is also pointing to that single node. TMP of next not equals to null. Condition is false because TMP of next is null. Because TMP is pointing to one first node and that is the last node. So its next is null. So you come out of this and then you write prev of next equals to null. Now prev is pointing to temp which is pointing to the first node. So prev of next is null. Yes, no issue for that. Then when you free up temp, so what's happening that you're freeing this single node. So that is also fine, perfectly fine. But you are returning H, and here comes the problem. H is pointing to something, a node which has been freed, and now we do not know okay, what's the content of H. Okay, so we need to make this as null. The moment we make this H as null, our work would be simplified. So how to do that? Any suggestion from your side? Yes, Daniel, that can be done. You can check with that. But now the question is about this. H equals to null, but where to do that and when to do that? Yes, after free temp. No, that way, if you have multiple nodes, so your list would become empty. अगर फ्री टाइम के बाद में आप एच इक्वल्स टू नल लिखते हो तो व्हेन देयर आर मल्टीपल नोड्स in that case your h should not become null. So you are removing all the nodes. You need to remove only the last node. And this is a special case when the first node itself is the last node. Here I need to put up one check if uh, can simply say if h of next equals null, then I would be saying h equals to okay, and else I would be saying proof of next equals to if h of next equals null, h equals to null, else proof of next equals null, and then split that. I think this should work perfectly. Let's check this code. Compile, okay, restart. Compile the code got compiled. Let's execute this. And here I insert a node, say 10. And then I insert one more, say 20. And then I display, so I get 10 and 20. And then I go for removing. So 20 is removed. Let's see. Yes, 20 is removed. Then I go for remove again. Now 10 should be removed. Last node removed. Let's see. Okay, so 10 is also removed, and now the linked list is empty. So now this is working perfectly. Okay, so it is handling all the cases, whether you have multiple nodes in your list or whether you have a single node in your list. This remove last function is handling all those cases. So this is my remove last function, which is handling all the cases, whether there is only a single node or whether there are multiple nodes. Okay, now then this logic is quite important. You should understand it clearly. If you understand this logic, then you can handle the two different possibilities of insertion and remove. That is, insert before a given node and then remove before a given node. Because in that case, you need this previous pointer. So with the help of this previous pointer, you can easily do that part. So now we have inserted the last node. Now you can, sorry, we have removed the last node. Now you can remove a node after a given node. You can remove a node before a given node, or you can remove the given node itself. So all those possibilities exist. So we can implement one more possibility, and then I would suggesting you people to implement the remaining possibility. But you should implement all the possibilities. So we are preparing for all. Now you tell me that which function we should write now. Three possibilities exist for remove. Four in fact. Remove first because remove last is done. Now remove first is pending. That is straightforward, simple. So I hope you can directly implement it. So out of three, we can implement now one. Remove the given node or remove after or remove before. Remove a node after the given node or remove a node before the given node or remove the given node itself. So please you give your choice into the chat box and then we can implement that function. Remove before, good choice. Remove before, good choice. So if we implement this, then you can easily go for insert before also because the logic would remain same. The way we are traversing the list, that logic remains same. Only instead of deleting a node, you need to insert a node. So that is a good choice. Remove before. So with the help of this function, you can do other functions also. Remove before, and what will be passing? We'll be passing the linked list, obviously. So the head point of the list, and this is remove before. So you need to search a given node. So a key value has to be there. So I call it k, or I can call it key, and then the return type would be obviously struct SLL star. Okay. The pointer to structure SLL. Now, what do we need to do? We need to search the given node k in the list, and we need to remove a node which is before this node, which is before this node. This is quite interesting. Okay, so let's have some dummy pointers. We also I need, and then if my list is empty, so nothing can be done. H is null. Printf list is empty. Return H, return null. This way I need not have to write else over here. That's why I'm writing return H over here. So then if the list is not empty, then we need to traverse and we need to find the given node. Okay. So traversing operation. So TMP equals to H, and then while I hope that you have understood that part of coding where we are writing temp not equals to null, and at the same time temp of data not equals to key. Okay. So here I would be writing slew equals to temp, and then temp equals to temp of next. Huh. So now, since this is removing before the given node, so there is a possibility that the given node itself is the first node. So when the given node is the first node, so in that case, you cannot remove a node before the first node. Okay, so that is also some sort of exception which you need to handle into our code. So when the list is not empty, and suppose the given node is the first node. So this condition would be true for the first node itself, and we may come out of this while loop. Okay. So here we need to check if the given node is the first node, then we cannot remove a node before the first node because there is no node before the first node. And here I can have a check if temp equals to h. Please try to understand this. What I'm writing if temp equals to h. Temp is pointing to the node which is having a value k. Okay, or temp is null if the k does not exist in the list. So suppose temp is pointing to the node which is having the key value. So temp is pointing to the given node. So after this loop, if temp is h, it means that the given node is the first node. When given node is the first node, there is no node before the first node, so you cannot perform the delete operation. So here, in this case, I can safely say printf no node before the first node. Okay. And here also we'll return it. Done. What is the next possibility? That the given node does not exist. So for that also, you can make up a code that is temp equals null. It means that the given node does not exist. So again, you cannot perform the delete operation. And here I need to simply say given node does not exist or is not present. Okay, so you have handled a case wherein the first node is a given node, then we have handled the case wherein the given node does not exist. And then finally, when you are at this point of your function, it means that the given node exists and it will exist, means it is not the first node. It is somewhere in between. And you need to remove a node which is just before that. And that node, as per our code, is pointed by the pointer prev. I repeat, that node is pointed by the pointer prev. So basically, you need to remove a prev node. What do we need to remove? A prev node. Okay. So now, what's the logic for doing that? Are you getting what I'm saying? You have come to this point. At this point, you need to remove a node which is pointed by prev. You have got that node. But to remove that node, you need an access of a node which is previous to that node, previous to previous. Okay. So again, we need to traverse, else we need to change the condition uh, into the above part, which is not feasible. So we will be traversing again. So here, let me write TMP of TMP. I am modifying TMP. TMP equals to H. And what I need to do, there is a preview pointer inside my list, and I need to only go to a node which is previous to preview. So while TMP of next not equals to preview. Okay, please see here. It's little tricky. TMP equals to TMP of next. After this loop, TMP is pointing to a node which is before prev, and prev is the node which should be deleted. Prev is the node which should be deleted, and TMP is the node which is uh, pointing to a node just before the prev node. So now I can say TMP of next equals to prev of next, and then prev of next equals to null, and then pre prev. Done. Temp of next equals to prev of next. Okay. So the next pointer of the temp has started pointing to a node which is next to prev. So we are removing prev from the list. Then prev of next equals to null, then prev. Now, your node which has to be removed can be a first node. What I mean to say that your key node is a second node. Okay. So in that case, you will be coming at this point, and then temp equals to h, while temp of next not equals to prev. So temp of next equals to prev because prev is the second node and temp is pointing to the first node. So we come out of it, and then we write temp of next equals to prev of next. Yes, and then we are writing prev of next equals to null. Perfectly right. Prev of next equals to null, and then prev. So whether our h is changing here, uh, till before prev would be the first node. No. Prev in that case would be the first node. If my key is the second node, then prev, which has to be deleted, is the first node. So we come here, tmp equals to h, and while tmp of next node equals to prev, so tmp of next is not prev because it is prev itself. So tmp equals to tmp of next. It will keep on going. It becomes an infinite loop. So what I need to do here, I need to say that TMP not TMP not equals to play, and at the same time, this is something like TMP not equals to null. Okay, and at the same time, TMP of next not equals to play. TMP equals to TMP of next, and after this, if after this here, if TMP equals to play, if TMP equals play, is a node to be deleted. I need to change h equals to h of next. And fine, I think this should work. This should work for all the conditions. Let us check that. Remove before, and where we'll be calling it. We can have one more option. Option number 5. Already removed before. Then display becomes 6, and my read becomes 7. So display is my case 6, and exit is our case 7. And then in case 5, Calling remove asking for the key value. This is remove before. Remove before. Okay, fine. Should be stopped. If I run, it will say code is running. I need to stop this. The remove before, insert before, all these before operations are little tricky. And if you handle the before operations successfully, then you can easily handle all other operations. Okay, so it got compiled. Let's execute. And then now let's check. I got suppose three nodes, 10, 20, and 30. Let me display. No, display 6. So 10, 20, and 30, three nodes are there. And what we'll be doing, we'll be going for remove before, and we'll be trying to remove one. Okay. And we'll go with the first option, remove before. And for remove before, the first possibility was the given value does not exist. Okay. So let's check for that key value, and suppose I say key value 40. So given node does not exist. Okay, perfectly fine. It gives us an error message. Given node does not exist, and we need to check whether the list is properly intact or not. Okay, so list is properly intact still 10, 20, and 30. And now I go for the same operation, remove before. And this time list was empty, check over, then list does not exist to be checked over. And suppose I give the key value is 10. So there is nothing before the key element 10. So whether our code is handling this condition or not, let's see. Okay, it is handling it. No node before the given node. Okay, perfectly fine. Let's see our list is intact or not. So display it. List is intact. Perfectly fine. Now let's go for remove before, and this time I suppose need to remove 20. So 20 is before 30. So let's go for that. And my key value is 30. Whether it's doing it properly or not. I need to check that. It is not giving any display message. It is not showing any message because we haven't displayed anything. Now let's display the list and see. The key value is 30. We have put up the key value 30 and the list was 10, 20, 30. So what we are expecting that a node before 30 should have been removed. So if 20 has been removed, so the list should be 10 and 30. So let's display it. Linked list contain on. Program terminated. So there are issues in the code. Before temp is H node that is working. This is also working. And Brave is pointing to a node temp of data not equal to Brave. Brave pointing to T and equal to H while temp not equal to Brave. It is not equal to sleeve. Sleeve is the node to be deleted. Uh, Here we are coming and 10, 20, 30. 30 was the given node. So sleeve is pointing to 20 before the given node. And now what we want to do, we need to reach to a node which is uh, before the previous node. While TMP of next not equals to true, TMP equals to TMP of next, right? Yes. So TMP is not true, and at the same time, TMP of next is playable. So TMP, okay, so TMP is continuous, TMP equals to 3. TMP of next is equals to 3 of next. Okay, fine. 3 of next is, yes, this code seems to be right. What's happening here? Oh, we are not returning H. Still, the H is not changed. Okay, let's execute. Today's session is more of technical type, almost I can say completely technical. So please bear with me. So I have inserted three nodes, and this is a scenario. Or link list is 10, 20, and 30. And I go for remove before the fifth option, and my key value is 30. And let me display. Okay, so now it has removed. Since we are not returning the value of H, only that was the problem. So now the node has been removed, and now let us remove before 30, which is the first node. So this should also be removed properly. I go for before remove before, and I again say 30. And yes, let me display. So yes, 10 has been deleted perfectly, and now we have only one node. And again, if I call the remove before and I say 30, so it should give me a message that no node before 30. So yes, no node before the first node, because 30 is the first node. Okay. So now we are able to remove before the given node with all the possibilities. So this code is working. Remove before function is working perfectly. But I still feel there must be some smart way of doing the same thing, because what I did, I handled one possibility one after another, and there can be a smarter way, more smarter way of doing the same thing. So I keep it open to you people. You can modify this code and you can make it the way you want it. And let me tell you that in my another implementation, which is available on the GitHub, I think this function is not implemented. I do not remember, but I think remove after is implemented there, but remove before the function is not there in that program. So what you can do that you can refer this code, okay? And I was about to come to that point regarding your lab part, and let me show you that. Before that, is there any query into this? Any query, any doubt? In fact, I would say that there should be some doubts, and there must be some doubts. And you need to see this code again and again. You need to practice it, and you need to change it or tweak it at your level. And then only I think you will be perfectly understanding it. Otherwise, yes, it is a little difficult to understand because now we are, trying to do it in a different way. For example, we are making use of the preview pointer. Then, when we are talking about deleting a node before the given node, so we moved one step ahead. We did not have only the preview pointer over there. We had one more loop where we traversed till the preview pointer, okay, or the node which is pointed by the preview pointer. So you need to practice this code. You need to do it again and again, and then only you can properly understand it. And you should practice it with different possible examples. The way I did it, for example, if the given node is the first node, if the given node is the last node, or the given node is any intermediate node. So you should check for all these possibilities, and you can check for all these possibilities on paper also. So it is not at all necessary that you must have a computer and you must code it there, you must execute it there. Yes, it becomes easy if you have that kind of setup. But even if you do not have that setup, and if you have only a code with you, then you can check it on paper also. Okay. So with the help of paper and pen, you can very well understand the code. You can check the code. You can go for different examples, different possibilities. That the list has only one node, that the list has multiple nodes, or the given node is the first node, given node is the last node, or given node does not exist, or the list is empty, or the given node is the intermediate node. So with all these possibilities, you can check your code, or you can check your function, whether your function is properly working or not, or the function is giving you the desired output or not. Okay. Then I wanted to discuss on this your lab part, and before starting that part, since the explanation for the today's session has been done, so I can stop the recording. Javed Khan Sheikh's Google Drive.